to all of you. Welcome to the first activity of the year and the semester. So over the last semester we had a lot of activities and we successfully organized the second Chem Week, which we had talks by various eminent scientists and a lot of fun activities, including tableau quiz, descriptive writing, sketching, just a minute. So our first event for this semester is a talk by the faculty coordinator of this club, Professor Viswanathan, and he'll be talking to us about chemistry. Let's welcome him.
Yeah, the topic is so general because she's asking me for a talk. I wasn't prepared. I just said, I was prepared for something, but she needed a title to put it up. So I said, say chemistry, and then I would say what chemistry can be, and then figured I'd talk on high temperature. The weather being so cold, you got to think of something to soothe you. So I said I will talk on high temperature chemistry, and that's basically what I'm going to do today. Some of the work we did a long time ago on high temperature processes and high temperature chemistry is what I'm going to be telling you today. The nice thing about, the interesting thing about high temperature chemistry is the fact that it behaves very differently from room temperature chemistry. So room temperature chemistry is always dominated by ground state molecules. The molecules in the ground state, they react in a reaction. But then in high temperature chemistry, when I say high temperature, it's not like 100 degrees, 200 degrees. I'm talking about 4,000, 5,000 degrees, 8,000 degrees Kelvin, and so on. And at such high temperatures, they're basically operating some of the excited states. And the chemistry that you now see is not ground state chemistry, but it's excited state chemistry, and which can be quite different from what happens in the ground state. In fact, when you look at excited state species, high temperature species, you will see that sometimes the valence rules don't seem to be obeyed. Many of the rules that we learn for So the high temperature species seem to have structures, molecular structures that we don't see in ground state or room temperature chemistry. Again, simply because we are talking about excited state processes. And that's a nice thing about high temperature chemistry. It also has relevance, and I will show you in many of our day-to-day lives. So that's basically the title, blow hot, blow cold, because we're looking at high temperature species, but we're using a low temperature technique. And you will see where the condensation really comes in quite handy. So we're looking at species that are high temperature species, but the experimental technique that I'm going to be using is actually a low temperature technique. And this combination is what lets us study the high temperature process. So it's study of high temperature chemistry, but we're using matrix isolation infrared spectroscopy. This is basically what we do. The matrix isolation technique is a low temperature technique. When I say low temperature, it's like 10 Kelvin. So we are actually looking at species produced at 4,000, 5,000, 10,000 Kelvin at 10 Kelvin temperatures. And we will see how we can have a marriage of these two very contradictory species. The topic basically is spectroscopy of cold molecules. So in this spectroscopy of cold molecules, there are two different methods by which you can produce cold molecules. You can have a supersonic expansion, in which you take molecules at very high pressure and expand them to a nozzle. They expand out to a nozzle, there's a cooling associated with it. And you can use this method to produce extremely low temperatures. You can get down temperatures like a Kelvin or a tenth of a Kelvin by such methods. The other method, it's a more subtle method, because in this method basically what we're doing is you're making the molecules do work, and with an adiabatic cooling that is associated with it. In the other method, which is matrix isolation, which is what we do, we basically trap molecules in an inert matrix on a cold finger. So we have a little window, we have a substrate that we cool externally by something like what we have in the house, the refrigerator. The refrigerator essentially, there's a post-cooling in a little chamber where we keep your food. So essentially what we do here is we forcibly cool a small tip and then deposit molecules onto this tip, and that's how we get the cooling. So here we produce a cold temperature and let the molecules equilibrate. In the formal exercise, we essentially let the molecules do the work and cool themselves off. So that's a more subtle method. This is the more brute force method. So about talking about supersonic expansion, I'm talking straight away about matrix isolation. What is matrix isolation? We mix the sample that we want to study. And today we want to study high temperature species. But otherwise, we mix the sample that we want to study with a large excess of an inert gas, like argon or nitrogen. We consider nitrogen as an inert gas because it doesn't really react in most cases. So let's say we're looking at acetylene and argon. And when I say large excess, I'm talking of an excess like 1 molecule of acetylene to about 1,000 atoms of argon. So extremely large dilution that we are looking at. So we take this gas mixture out here of acetylene and argon, 1:1,000, and we let them expand into vacuum. And this is not a very high pressure, so there is no expansion and cooling and so on. The molecule just diffuses out and they get into the vacuum system. And here I have a substrate which is a potassium bromide substrate. Why potassium bromide? Because we are looking at infrared spectrum. So we would like to use a substrate which is infrared transparent. The molecule just freezes out on this at 10 Kelvin, and therefore at 10 Kelvin everything except hydrogen and helium will freeze out. So argon will freeze, helium will freeze, acetylene will freeze on this substrate. This is a further vacuum system. Now because I used a large excess of argon and a very small concentration of acetylene, the whole thing freezes out, what will you see? You'll see argon everywhere. So these policemen here are argon, and acetylene will be sitting in some locations away from each other. And this has happened simply because of the dilution phenomenon. I've used 1:1,000 ratio. So there's argon everywhere, with acetylene sitting here, there, and somewhere. So there are no two acetylene molecules talking to each other. It's acetylene molecules isolated from each other. The only thing that they are even looking at is argon around them. And for first approximation, if you assume that argon is inert, then acetylene basically has inert partners. So it's sitting in an inert environment, cannot react with anything around it. It's sitting at 10 Kelvin and it's sitting isolated. It is very different from a normal sample that you encounter in infrared spectroscopy, like a solid or a liquid, where acetylene molecules in a gas phase, for example, are colliding with other acetylene molecules, and you have a situation like this. Whereas here, they have all been isolated from each other. You are essentially trapped into little cages, and the cage itself is inert, and therefore acetylene is sitting in an inert environment with no interactions whatsoever, and at a temperature of about 10 Kelvin. Now at 10 Kelvin, what happens? You have all the molecules sitting in the lowest vibration state, instead of the lowest rotation state. So it's basically energetically cold. They're not colliding with anybody. They're not moving. If they're not moving, there is no Doppler width, no Doppler broadening. They're not colliding, there is no collisional broadening. They're all sitting in this one level. There's only one transition, B0 to B1 and maybe J0 to J1. Whereas at room temperature, you have maybe 1 or 2 vibration levels populated, many rotation levels populated, and you therefore have a large number of rotational transitions like what you have here. This is a gas phase that's sitting at room temperature. There are many rotational transitions, J0 to J1, J1 to J2 and so on. And we have learned that there is a most probable J, which is what this is, and these are the P and R branches for acetylene. But in the temperature of the experiment that I just described, which is 10 Kelvin, there's only one transition that you will look at, and therefore J0 to J1, everything else is suppressed. You therefore have extremely sharp spectra as opposed to very wide spectra that you would see under normal room temperature conditions. So this experimental technique essentially provides for you extremely sharp spectra, and that's the big advantage. Spectral width is one advantage. What's the other advantage? I'm basically trapping molecules in an inert environment. And you will see it is one aspect that we're going to be utilizing when we study high temperature species. The experimental method is as follows. Here's the Fourier transform infrared spectrometer which is used to record the spectra. This is the cryostat, so this is from the earlier lab that I worked. We now have a similar setup here in IISER Mohali, which I have not brought here. But a very similar setup has been now installed over here. We're already using it to study hydrogen bonding complexes of various systems. And this is a little chamber in which you mix your acetylene and argon at the appropriate concentrations and then stream it through a little valve into the system. And this is the cryostat which basically produces the 10 Kelvin. It's a little nozzle through which the gas actually diffuses out into the vacuum system. It's a mixing chamber. can you do with this sort of an experiment? Well, since the line widths are so small, you can study molecular conformation, which we did, organic phosphates, acetals and ketones, and cell analogs. We can study weak complexes like hydrogen bonding complexes, van der Waals complexes. These are things that you can study with the experimental setup I showed you. Today we are not looking at these, we are looking at studying high temperature species with the experimental technique that I showed. How do you do that? First of all, why do you need to study high temperature chemistry? Well, you need to study high temperature chemistry because there are many nuclear reactors where high temperatures are very often encountered. In a fission reactor, for example, it's high temperature, essentially. Only under those conditions can you, in fact, get fission to go. So, which means you need to understand high temperature behavior of materials that are used in a fission reactor. In a fusion reactor, it's in a fusion reactor. In a fission reactor also you have high temperatures because the core is actually at pretty large temperatures and it's not at 5,000, 7,000 Kelvin, it's maybe a order of hundreds, 600, 700 and so on. But the problem is, should there be an accident? Let's say there is loss of coolant in the fission reactor. The temperature of that core, the nuclear core, will actually rise to about 4 to 5,000. You have to know how the material which contains the core will actually behave under those conditions. This is an accident condition and you have to see how it behaves. If you know how it behaves, then you can actually factor this into the safety factors when you build the nuclear reactor. And that's important. And that's the reason why high temperature studies are extremely important for the nuclear reactor. This is where I worked and it was important. And then we had a study in some of these things. Modeling high temperature behavior of fuels and structural materials. You have to know how these materials will behave at 5,000. At the time of an accident, you can't have surprises. Therefore, you need to know it much before as to how these materials behave, so you can factor these data into the building of the reactor itself. Aerospace industry needs high temperature data. Anytime you have an atmospheric re-entry of space vehicles, the temperature actually goes to many thousands of Kelvin. Therefore, you need to have a clear idea of how the materials that actually make up the structure of the vehicle will actually behave under these conditions. Therefore, you need to know for the aerospace people high temperature behavior of materials. And finally, of course, there is a lot of fundamental interesting chemistry that happens at high temperature, and therefore we would like to know. High temperature chemistry is sometimes very exotic. It doesn't behave as if the ground state molecules behave, as I said earlier. What's the problem in doing high temperature chemistry? Let us say you want to study materials at 4,000 Kelvin. What's the problem? First problem is attaining high temperatures like 4,000. It's very easy to attain temperatures like 1,000, 1,500, even 2,000 because there are furnaces, there are materials that you can get, resistive furnaces that you can get. You have a coil, pass current through it, and you can get your 1,500 to 2,000. But by the time you get to 4,000, it's not so easy. It's extremely difficult to get 4,000 Kelvin because there are no structural materials that will actually survive these 4,000. Most materials will actually melt by them. That's a So simply attaining 4,000 Kelvin is an issue. The next one is the container problem. If I want to study, let us say, an oxide of a material. Let's say I want to study a lanthanide oxide, European oxide, and its behavior at 4,000. What do? I take it into a container and heat the container. But if the container melts before 4,000, then I don't have an experiment. It's basically as silly as trying to boil milk in a wax vessel. Before the milk is boiled, the vessel is gone. And therefore, there is no boiling at that point. Therefore, you have a container problem. So 4,000 Kelvin is a container issue. You can't get the experiment going to 4,000 K because the container in which you take the material would be long gone before you got to 4,000. What's the solution? Laser ablation. And what is this technique of laser ablation? It's the following. Let's say I have a material whose high temperature behavior I want to study. I come in with a laser and I focus it down onto this material. At the tip where you need to focus the laser beam. The laser beam is actually focused down to, let's say, about 50 to 100 microns. And if you have sufficient energy in the laser pulse, then the energy density at the focal point is quite high. And when this hits the spot, you will actually produce 4 to 5,000 Kelvin or even 10,000 Kelvin, depending on how much energy you have put into the laser beam, how tightly you have focused it, and how short a pulse you have. These are the parameters that are under your control. You can actually get up to 4, 5, even 8 to 10,000 Kelvin using a laser beam. So it's not a resistive heating, it's a laser beam. It's very trivial to produce such high temperatures. All you need is a laser beam of sufficient intensity and the ability to focus it down to extremely sharp focus spot sizes. And when this tip over here goes to 4000 Kelvin, let's say, or 5000 Kelvin, the material will now respond the way it should respond at 5000 Kelvin. It produces vapor phase species, and if I have graphite, for example, it might produce a C2 cluster, a C3 cluster, C5, C7, all sorts of clusters, which it should rightfully produce when the temperature goes up to 4000, 5000 Kelvin. If I go to 10,000 Kelvin, a different set of species might be actually thermodynamically stable, and they will be produced. So I can actually vary the temperature on this focal spot where I am hitting the sample with, and by varying the temperature, I can actually vary the species that are produced and get an idea of how the sample actually behaves under various experimental conditions. So if it's a structural material in a reactor, all I have to do is to take this to various temperatures and see what species are produced, and thereby get an idea of how this material will actually behave at these very high temperatures. So the point is, the laser ablation technique is actually a pretty simple method by which you can get very high temperatures.
Excuse me, sir.
Yeah.
So was this the setup which was used when full range were discovered?
Absolutely. This was the setup that was used when Smalley used, when he produced C60. Actually what he did was, he had this, but then of course I showed you that it's only C2, C3 and C5. How do you get C60? What Smalley did was, he had this ablation going on in a high pressure chamber. So in a high pressure chamber there are collisions, more collisions. So the C2 will collide with C3 will collide with more, and the cluster will start to grow, and finally you will have C60 that was produced.
Even that, was that also focused on a cold single?
No, it's not focused on the cold thing. It is focused on room temperature material.
The condensation of the...
Yeah. In Smalley's experiment there was no condensation. All he did was, he produced these clusters and sent it into a mass spec, and then saw what mass he was getting, and he got 720, and that told him that they had C60. So he was not really condensing